And then
so there's a small change in the Canvas syllabus, mostly to be more in line with some of the other instructors are doing. We went this morning to talk about it a little bit. The quizzes are going to be 20% of your grade now. I'm not going to change the number of quizzes. However, if you are not feeling like you're doing well with those quizzes, instead of having that final project that I was talking about be its own 15%, it's now going to be 10%, and you can add that into the quizzes. So if you're not doing well in the semester with your quizzes, at the end of the semester, you can work on that project and submit it and get up to 10 points added. So now the project is more like a bonus project rather than actually part of your syllabus. And then that way, if you're doing well in your quizzes, you don't have to worry about doing it. And in my mind, if you're doing well in your quizzes, my shifty way of getting you to study more for the final, you probably don't need to do as much with that final project. You can still do the final project, obviously, but you don't have to worry about it quite as much. The homework is 10% instead of being homework and quizzes combined with one another. And like I said, I haven't updated Canvas to match this yet, but I'll be doing that sometime this afternoon. And then if you have any questions regarding that, let me know. Otherwise, we will get into our material. Did everyone see that I posted the homework one on Canvas? It should have sent out an announcement. Okay. At the very bottom of that, there are some self-study problems. Those can also be suggested problems, but I find suggested problems to be a little bit lacking in the importance. Just doing the homework set will not be enough to prepare you for the exam. That's to give you some incentive to do problems all the way through and well thought out, and so that I know you know how to do problems well thought out, and so you get some feedback before the exams on your work. But in terms of depth and like broad aspects of covering the material, be sure you look at those additional homework problems. Those are from the Wiley Plus textbook. I know the solutions are everywhere online, which is part of the reason why I'm not asking you to put those in. But a lot of those solutions can be step-by-step solutions, and that will help you as well. If you do have questions on those problems, let me know. When I have a final review session, I might work some of those problems, especially if they're ones that you have more questions on and you have, like, I can work through those. So don't stop just at the homework that you're supposed to turn in, but I don't want to enforce that because your timeline is probably different than the timeline that I would set for turning those in. If you know yourself and know that you're going to have trouble motivating yourself to do those, let me know. We can come up with some kind of like organizational scheme for you to get that done, something that's not graded, but maybe to help motivate you to work through that. So we talked about theory of rectangular coordinate system and worked a few example problems. You'll have more in your homework. And also, and some of you may know that statics used to be statics and dynamics. And when I was teaching it in spring of 2020, everything went online. And that was the start of the dynamics portion. So I made a lot of homework videos that I posted on YouTube for chapters 1 through 3 in the dynamics section. And they're based off of the Wiley Plus homework problems. So some of them are going to be the ones that are suggested problems. And I work through them in detail. You might want to skip the first handful because I get a lot better as it goes on. But you still might find the first ones helpful. I've questioned whether I should take them down or not because I just don't like them and it's embarrassing, but I do think there is some help in them. But know that they do get better. I've posted the link for this. It's remote engineering where the E's overlap. So clever. It felt so clever. The only thing I can think of is there's probably a reason why people haven't used this before. But anyways, the link is on Canvas. You can also just search it. And there's also a couple reviews on there as well for chapter 1 and chapter 2. You might find that helpful as we get closer. I'll still do my own review session, but that might help you some. Some more examples on rectangular coordinate systems there. Also, before we move on to the normal and tangential coordinate system, I want to make some comments about organization of variables for this section because there are a lot of variables to organize as you're working through these problems. And last time I kind of said you can organize it in your own way. Well, now I want to give you some examples of different ways that it can be organized. I typically will always organize it in columns for time, even if it's just like x naught equals some number, x final equals some number, even if I just like have that on its own. I usually put them next to each other, not always. And then for the rows, you can segment off x and y completely separate. So you have x, v of x, a of x. All of these are 1, x, v of x, a of x. All of these are 2, x, v of x, a of x, and all of those are 3. Because there are some problems that you'll have more than one time change. And then you can do the same thing down here. Y, v of y, a of y, y, v of y, a of y, y, v of y, a of y, where this first column is 1, second column is 2, third column is 3. If a problem says that there's like a time instance, you have like time 1, time 2, time 3 in some form or fashion, you know that all of these variables are possible. Then you can look further in the problem statement to find that, oh, this is constant. So AX 1, 2, 3 is the same. oh, this is equal to 0. Vy is equal to 0. These are equal to each other. You can go through and identify what's actually going on. This is one of the few topics where the theory and derivations is actually easier than working the problems, just because the problem statements have so many varieties in the way they are stated. So this is one way you can organize these variables. Another way is to put the x and y within one another and organize it by position, velocity, and acceleration. So I would have position, velocity, and acceleration, x, y1, vx1, vy1, ax1, ay1, and then you would do the same things for 2, ax2, ay2. So here's all the same variables, but now it's organized in terms of position and velocity and acceleration. And then don't forget too that sometimes instead of x and y, you might have two different objects. So you can always replace the x with, let's say, object 1 and y with object 2. And then that's going to come into play when you look at the suggested problem. Sometimes there'll be two objects that you're trying to relate to one another. Even though you only care about them in terms of time, there's not a connection in terms of theta. You can still relate them by having these two different sections. It's best if you find one way and keep it consistent and do it that way every time. Obviously, you can get the right answer if you don't do that. But if you do stay consistent when you're working the homework problems and such, when you get on the exam, you'll have a little bit more of a pattern. And so if you're confused by the problem statement, you can still start your system. And then maybe as you get further into the problem, you'll know where to go. Any questions on this? Okay. Yeah, so be sure you work example problems. This is one of the few topics where the theory is easier than working the problems, because for some reason these problems can be pretty complicated. Now we will move into normal and tangential. Normal and tangential is a really helpful coordinate system in dynamics where everything is about motion, because the normal and tangential is based on velocity and everything about it is dependent on the direction of velocity. And static, sometimes normal and tangential were nice to use because you could see that there was some kind of motion around in a circle or something like that. But here it's all focused about the velocity. And even though the sum of the force equals mass times acceleration, this is acceleration, not velocity. Originally, before this problem is simplified, it's a momentum equation. So it's the change in momentum. That's where it started from, where velocity was of utmost importance. And then when the mass did not change, then it becomes simplified into acceleration. So to keep in line with velocity being of the utmost importance, when we look at a velocity vector with the magnitude and the direction being separated, we're going to find a coordinate system where one, the tangential, is all about the magnitude, and the second, or normal, is all about that unit vector or the direction of this vector. Whereas the other coordinate system, x and y, that's dependent on the physical position of your objects. Gravity is in the y direction. If we're normal and tangential, gravity, it does not matter where it is. If velocity is going along gravity, then that's great, but it's not dependent on gravity, it's all dependent on velocity. And this should really be a vector, because then when you break it down, if I was to take the time derivative of this, we have two objects that change with respect to time. You can change the speed of an object with respect to time, and you can also change the direction of an object with respect to time. This is where it becomes more complicated than X and Y, because now we have a product rule. We can't just separate them and take that derivative. So then you have the product rule, taking the derivative of that velocity first, plus the velocity, and now we're taking the derivative of that unit vector. This is easy in terms of what we've already seen. We can treat this as a particle where the distance traveled is s, so it doesn't matter if it's in a straight line or all curved and cattywampus. This only has to do with the speed. What is much more complicated is taking the time derivative of a unit vector. There is a really, really nice long derivation for this. And I know that I had questioned about making a video of it in 2020. I can't remember if I did or not. I know I made a video of deriving this side because it's easier. If you are interested in the derivative of the unit vector, let me know. I'm not going to work through it. Instead, we're just going to talk about it in abstract terms. For some reason, with the unit vector is typically referred to as E hat instead of U hat or I hat or whatever hats you're used to. It's typically referred to as E hat. So if the tangential of E hat is going in the same direction as velocity, this side will be the velocity E hat, or sorry, acceleration. This is the tangential. It's in the same direction as velocity, and that is how we are defining the unit vector to be in the same direction of velocity. That's a given that we have predetermined. And then this is our acceleration. To be more clear about what kind of acceleration this is, and I really like to be more clear, you can put a t, a sub t, because this is the acceleration that is tangential to that velocity. So our like non-directional particle acceleration that we saw before. Then when we get here, we have velocity times e t hat dot, where the dot is the time derivative. I don't usually use dots, but for this, it makes it a little bit easier to see. This is a change in theta here, because our unit vectors can be defined with cosine theta, sine theta, 0. They can also be defined with percentages, but here let's just think about it in terms of theta. So it's a time change of theta, but what we know is that there can be a line that is 90 degrees from E sub t. And if we consider changing this theta in terms of a 90 degrees using some fancy trigonometric identities and substitutions, we can change it to where ET dot is equal to V over R E in hat, where this is En. That perpendicular is En. So it's a function of velocity over radius. This radius is kind of exactly what you would imagine is a radius going off of our tangent. So it's some kind of radius off in this direction. If we didn't know that radius, we wouldn't be able to calculate how much it's changing in terms of theta, so that radius is required for this derivation. We can take our E sub t dot and replace E sub t dot here. And we'll get an equation that might be familiar to you from physics, v squared over r. Where this v squared over r can be written as an. And a lot of the homework problems and maybe even exam problem, there can be sometimes information given to you about the acceleration, and you're supposed to find r or rho for radius of curvature. And you do that by finding the normal acceleration, and then you can convert back and forth between radius and acceleration and velocity as well. Any questions on this simplified derivation of how we got here? Hopefully this will give you some more context of what you're doing and why these equations are helpful. I know that you can use these equations perfectly fine without having this, but I think it's helpful, so you might as well. There's another substitution that we can do, and this is for curve linear. And this was technically the topic that we were supposed to talk about last class, but I really like to talk about it here because it has to do with radius and rotation. With this, we can find that v is equal to r omega, where omega is angular velocity, radians per second. It can also be in degrees per second, but you'll want to convert it into radians per second before using it in one of these equations. If we take the time derivative of this, we can get acceleration equals to r alpha, and we can substitute both of these values into the rectangular coordinate system and into the normal and tangential coordinate system. For normal and tangential, where the velocity is equal to the magnitude of velocity times E sub t, remember we've defined it as this way, you can substitute r omega E sub t. For acceleration, you'll have the acceleration tangential E sub t plus v squared over rho. I'm going to use rho instead of r because rho can be used in much more applications where that's the radius of curvature. E sub n hat. Substituting rw and r alpha E sub t, r omega squared over rho E sub n. Then for x and y, theta equals theta dot plus omega dot t plus 1/2 alpha t squared. And in your homework, you're asked to derive these. You can start that derivation with these two equations here and the derivations from the previous part where you get the x and y values and then substitute them in here. So this next part isn't too much of a step, but note that it also is on your homework. And then omega naught plus alpha t, omega squared equals omega naught squared plus 2a theta minus theta naught. So we can also work problems in angular sense These come in really handy when we're looking at moments, because with a moment, some of the moments equal I alpha, where I is inertia, and alpha is now in our equations. So that's now helpful. And that acceleration is definitely supposed to be alpha. Here we go. Yeah. Don't mix them like I did. Which is nice to have equations in your arsenal, but it's also not nice because now probability statements can ask for a variety of things. Where in statics, the questions were a little limited since we could really only ask about forces, which I'm sure it did not feel limited at the time. But looking back, you might see that. Any questions on these derivations or equations? And remember, you do get an equation sheet, so it might be helpful for you to start working on that equation sheet, just putting down things that you need. You can fix it up later, take things off when you realize that you definitely have it memorized and whatnot. Before we move to example problems, I do want to talk just a little bit more about the normal and tangential and how the velocity vector completely defines where E sub t is. Therefore, it also completely defines where our A sub t is. No matter which direction this curve is going, whether it's the like outside or inside, your normal coordinate system is always going towards the inside of the circle. If we had some kind of slope like this, you're calculating at this point, and hat goes towards the center, towards the center, towards the center, and upwards. So it always changes direction based on the velocity and what's going on with velocity. So as it goes around the circle and it's rotated, it stays in line with the circle. The whole entire coordinate system changes based on where that velocity is going. Unlike the X and Y, where that was completely based on the position of objects in the room, this is totally dependent on velocity. So the direction of your AT and your E sub t, that completely changes as velocity changes. It might be something that you're able to see right now pretty easily, but when you're doing a homework problem, it might be tempting to fixate on objects that you can see in the room. This is much, much more abstract than any coordinate system we've done before. A coordinate system that moves within the room. And as we get into relativity, not only does the coordinate system move within the room, but your velocity can be relative to many different objects. So it just adds a whole nother level, which I think is fun. You don't have to, but I love it. Okay, now let's get into some example problems. And this first example problem, we're talking about a hill that changes in direction, kind of like I just talked about. So at here, position A, E sub n will be going towards the center. Over here at position C, E sub n is now going downwards. There is a point here where the direction changes. And at that point, rho is infinite, meaning that it's a straight line. If rho is infinite, that circle just gets bigger and bigger and bigger and bigger until you can treat it as something that's flat. Mathematically, that's the idea, but we will just call it a straight line at this point here where it changes. And that takes us back to the apex, where if it's positive and negative, there has to be some point in the middle where it's zero. So we have that kind of slope going on here as well. There is a car driving and it follows this exact curve based on the hill. At velocity of A, this car is going 100 kilometers per hour. And for this, we're going to treat it as particle motion. So we just have to have v of A. We don't have to have VAX, VAY. And we have one particle, so that's going to make it a little bit more simple. And at C, this car is going 50 kilometers per hour. And we'll need to convert these to meters per second, which we'll do in a second. If the total acceleration at A, so this is the magnitude of the acceleration. That's another word for total, or for magnitude is total. Is 3 meters per second squared. And the radius of curvature at C, let's move these down. Is 150 meters. We already talked about the radius of curvature at B being infinite or straight line. We are to calculate the curvature at A, or we can put like a little box so we can fill that box in. The acceleration at the inflection of point B. So acceleration at B, also solving for that. And the total acceleration at C. So notice we filled this in and it doesn't give us anything about V of B, the velocity at B. So we don't know if we need to solve for that or not. It didn't say anything about it, but that might be a stepping stone. So we can go ahead and just fill in that we don't know what it is, but those squares will indicate that that is what we are looking for. An interesting note about the acceleration at B, it asks us about the total, or it asks us for the, what's the exact word? It just asks us for the acceleration of the inflection at point B. But we know the radius of curvature there to be infinity, so there is no normal acceleration. So what we can also say is that we know this to be the tangential acceleration. Because in this instance, the normal acceleration is equal to 0. Also note that I switched to N and T, whereas the derivation of these equations heavily go by E sub n and E sub t. As soon as you leave the mathematical derivation world, they are typically written as n hat and t hat. So that's how I'll be writing these. Your textbook, I believe, continues. Well, I guess there's no figure here. I think your textbook continues to use the E sub n, E sub t sum, but I don't want to write that out every time. So I'll use n hat, t hat. You can use whatever you want to on the homework. I'll accept both. I'd mentioned before that we would convert the velocity of A, and let's do that. 100 kilometers per hour, 1 hour, 360 seconds, 3,600 seconds, 1,000 meters kilometer, and that will give us a velocity of A of 27.8 meters per second. Velocity of C will simplify to 1,000 over 3,600. And the velocity of C is equal to 13.89 meters per second. So I'm going to come back to our original. You can rewrite it, write it next to it. But for now, to keep this clean, I'm going to rewrite our given values of something that's actually useful to us. So 27.8 meters per second. And since we can treat this velocity and AT as simple particle motion, not caring at all about the direction it's given, we'll use the equations that we've seen before with v squared A equals bc squared, or let's write that the other way. So v squared VA squared plus 2AX. This, well, let's say S because it's not really a. I realized that I have left this off. So the total distance traveled from A to B. We don't care that it curves. It's the total distance. If we were to have a measuring tape written out in this way, the total distance is 120 meters. Why was it so hard to add that? Yes. So this is a nice equation. We know VC, we know the velocity at A, and we know that this distance from A to C is 120 meters. It's important to note what this acceleration is. So this is the tangential acceleration because it is defined to be in the same direction as velocity. And we are also solving this for the final position. So this will be the velocity at C. So 1 over 2s times vc squared minus va squared 1 over 2 times 120 times 13.89 squared minus 27.8 squared. And this acceleration is going to be negative 2.41 meters per second squared. So what this tells us about the velocity is that it is going in the opposite direction. Or sorry, what it tells us about the acceleration is that it is going in the opposite direction of velocity. So that means that velocity is decreasing. It is slowing down. Remember that this does not tell us anything about the direction. Yes.
Continue what you're saying.
It doesn't tell us anything about the direction in terms of if it's like going upwards or downwards or left to right, because the velocity could be going left or right. It only tells us that the velocity is decreasing. And this is a little bit like tension and compression. It doesn't tell you which direction those arrows are. You still have a positive and negative to define tension or compression. So that is this negative sign here, defining speeding up or slowing down, not any kind of direction in the space of the room or yard or road. Yeah, what was your question?
My question was, like, the coordinate system, like, the reason that we're defining it around like the object, is it's because then you can just add up these different velocities together more easily, because otherwise you have all these like different vectors that are always changing based on like if it's going up the hill or whatever. Is that kind of the idea?
So I think I know what you're asking. Correct me if I'm just like totally not hearing what you're saying. Yes, it's really helpful. If we were going with X and Y, this one wouldn't be too terribly bad because there are two moments where our velocity is horizontal. But at this point in the middle where the velocity is not horizontal, then you have some components of theta and you can't separate the magnitude, like the speed and the direction as well. And speed is really easy to measure because you look at point A, point B, and you have a timer and you can measure how long it takes to get there. But the direction during that time is complicated. So if we tried to get a stopwatch and also measure theta, which is what we would need, it would just be annoying. So I think the answer is yes to your question. We can talk about it more later though. And I'm sure we'll kind of address that as we go on. But yes, it makes it a lot easier to handle particle motion with normal and tangential. And then with forces, it doesn't really matter which one you use because they're both 90 degrees from one another. It's kind of like if you take it, we'll get there. Slowing down, opposite direction of velocity. Velocity could be going in any direction. Okay, so this acceleration is the acceleration tangential of our particle slowing down from point A to point B. Okay, and we're going to use that as we go on because this does not change. In the problem, we are assuming constant acceleration. These equations are assuming constant acceleration. So that's something that we just have to assume for our problem is that there is constant acceleration in this problem. So that first part where it asks us to find the radius of curvature at A, that's looking for this row. We have velocity. Now we have A sub t. What we can find from velocity in A sub t is A sub n because we're also given that the total acceleration for this location was a value that we can pull back up here. So we were also told that the total acceleration of this location is 3 meters per second squared. So we have two of the accelerations if we were to use Pythagorean's theorem. A normal squared plus A tangential squared. This acts like any other 90 degree with a vector in the middle. We can use Pythagorean's theorem. If you're wondering why I wanted to get this tangential acceleration, my first answer is that when dealing with velocity, and you're given a time and a distance, it's very wise to get the tangential acceleration because you're going to have to use it at some point. Yes.
So the tangential acceleration is solved for, that's also the acceleration B, correct?
Yes. Yes. So the first one is, in these problems, you can just kind of solve for it always if you can. The second answer that I would give as to why we solve for the tangential is because when looking for rho, we know that we need to get a normal, and we were given, we were given the magnitude of the acceleration. So in order to get a normal, we need to get a tangential. So being familiar with where you are in the equations can be helpful to figure out where you're supposed to go. But it's always something that if you can solve for it, you probably should with the tangential acceleration. So here you are with our Pythagorean's theorem. And I just wrote this down, v squared over rho squared plus at squared a squared. I'm actually not going to carry the variables through. If I was on my own, I would, but that gets kind of messy here. So let's break it down into smaller parts. So looking back up here, the magnitude of the acceleration at A is 3 meters per second squared. 3 meters per second squared. Our AN right now is what we're solving for. AT negative 2.41 squared. And AN will equal 1.785 meters per second squared. Then we'll use v squared over rho to get rho as v squared over an. The velocity was given to us at point B. So this was given, point A, 27.8 meters per second. And that is what we converted the velocity to because it was originally given kilometers per hour. So 27.8 squared over an, which is 1.785. Rho is equal to 432 meters. So for this section of part A, we were asked to find rho at A. Yes.
So rho meaning the curvature,
Yes.
432 meters, what is that diameter, radius, circumference?
Radius.
Radius.
Mhm. So this would be radius if a perfect circle. So if it was perfect circle at this location, it would be 432 meters. So originally asked to find P of A. We knew that we had the magnitude of A. We knew that we had velocity of A, velocity of C, and distance. So we used that to find A sub T. We used both of these to find A sub N. We used A sub N to find rho. And this is a very, 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 very common path that's taken in these dynamic problems. Sometimes they might give you different information, but going from the tangential and just overall acceleration, you then get to normal, and then you get to rho. Sometimes you might be asked to solve for this if they give you acceleration in the y, acceleration in the x. You can use these to get the magnitude, because the magnitude is the same regardless of which coordinate system that you use. This problem didn't get us to go in that much detail, but sometimes it may. Any question about part A before we move on to part B? Okay, so the next part is to find the acceleration at point B, which we already talked about, rho being infinite, therefore it is a straight line. Therefore, this is pretty much the tangential. If all of the acceleration is tangential and there is 0 normal, and we know from earlier the total acceleration that's constant from A to B, then we immediately know that the total magnitude of the acceleration is going to be the magnitude of the acceleration at B. You don't need to do all of these steps to get there. But showing the importance of knowing straight lines is incredibly helpful, because you have a velocity traveling in a straight line, you don't have any normal. So it makes the Pythagorean's theorem kind of useless at this point, because it's just the same. So for this last part at C, there is a velocity here, and this time we are looking for the total acceleration at C. Unfortunately for us, or fortunately, depends on how much you're enjoying this. There is a number for the tangential and there is a number for the normal. So we can't simplify it down as easily as we did before. What we do know this time, opposite of what we knew before, is we know the radius of curvature this time. For point A, we did not know the radius of curvature. Here we do. We also know V sub C. So the radius of curvature at C being 150, and I don't remember what V sub C was, but we'll find that in a second. We now know this point here. We know our normal. So we can work through this part. AN equals 13.89 squared over 150. That is 1.286 meters per second squared. And the value that we got earlier for tangential, the negative 2.41, we calculated that at the beginning using velocity of A, velocity of B, the 120 meters traveled, and yeah, that's all we needed. 1.41 for tangential acceleration plus 1.286 for our normal tangential, our normal acceleration. That is our vector, but we're looking for the magnitude of this section. The magnitude being the square root of the sum of the squares. So negative 2.41 squared plus 1.286 squared. That will equal 2.73 meters per second squared. Part C is exactly opposite of part 1. So here we're actually looking for the magnitude of our acceleration in total. We're given rho and we know the velocity of C. So from that we can get AN. Again, we are given AT from that calculation earlier. And from here, we can calculate the total acceleration from C, A, and S, which was that 120 meters. Being able to go both ways is incredibly important for this part. And now that we know all the values, let's go back to our lines and put these all in. So for our A normal, we found this out to be 1.785. And our A tangential, we found to be negative. So that's 2.41 in the opposite direction of the tangential. Therefore, the magnitude would be going somewhere in this direction. And this one's boring tangential. AT for B is just negative because it's a straight line. And then negative tangential is still the 2.41 meters per second squared value. A normal, we calculated with V squared and 150 meters. That was 1.286. And then the magnitude was 2.73 meters per second squared. Yes.
So the tangential acceleration is the same on all 3 points.
Yes.
How does that work? That can mean every single problem.
For this class, yes.
So that's-
Except for, let me give a long explanation. This is a great question. In this class, we've decided that there aren't going to be significant changes in acceleration as we go through. So the acceleration between A and B and the acceleration between B and C is mostly the same. And that's just something that for this class, we decided. And all of the equations that we've calculated, no, that's not. Like the VC squared, VA squared plus plus 2A. No, that was right. Okay. So all of these equations that we derived and that I'm asking you to derive in the homework, that's assuming constant acceleration. In the suggested problems, you will come across a homework problem that your position is given as like a function of t, and as you derive that down, you'll get acceleration as a function of time. So it is like exponentially growing or something like that. That is as close as we're going to get to changing acceleration. Those problems are more to say like, hey, it's not always constant, just remember that. But there's enough that we can look at with constant acceleration. Yes, so great question. Not always true, but it's kind of like a lot of times when you assume, do what? Yes, yeah. And for the purpose of this class, you will be very happy to have constant acceleration. Although hopefully I'm giving you enough understanding of where the constant acceleration equations come from, so that in the future, when you do get equations that are not constant acceleration, you know how they fit into what we're doing now. Because like when you get into system dynamics and controls, you won't have constant acceleration then. So being able to know where these equations come from to like backtrack and fit them together is really helpful. So if you are finding these derivations helpful, I think that will benefit you in systems later on. If you could remember that, because that's like 2 years from now if you don't co-op, or if you do. Yeah, so just good luck. Great question. Any other questions regarding this problem? Okay, yes.
Can that normal acceleration be understood to be the amount of force it takes to create that curvature?
Absolutely. Yes, that is 100% right. And when we get into kinetics later on, remember that, because the way that your like car moves as it's driving, when you feel force to the right and to the left, yes. Part of the reason why centripetal force is like not a thing. We will get to that pet peeve later on. Yes, the force that turns you left and right is normal acceleration, not centripetal. That does not exist. Although it's like one of those things like deceleration, like everyone uses it. So it's like, you know, it doesn't exist, but I know what idea you're trying to say. So yes, and I'm not gonna like stop this dinner conversation to like explain that to you. I have to learn that there's a time and a place. I think that is probably one reason why most of my friends are engineers, because they're like, oh yes, let's talk about this. We're going to start this next problem. We will not finish it today. We have 15 minutes and not enough time, but that's why I wanted to start this normal and tangential, so that next time we can work through more example problems, because this topic is incredibly important. Miles per hour. This is a rocket, as you can see from the little rocket coming out the back of it. And when we've looked at projectile motions before, we did not consider any kind of like horizontal acceleration, but here we want to, and we're not doing X and Y, so it's going to be fine in terms of calculations. So here our rocket is horizontally accelerated 20 feet per second squared, and that is horizontal. Even though it's getting accelerated horizontally, it's traveling like downwards and forwards. So this is our, and I realize that this arrow should be dashed. This is the horizontal. Horizontal. Okay. And our velocity is along the tangential acceleration, or the tangential acceleration is along the velocity. I kind of like it that way, I guess, because velocity comes first, then the definition for tangential. So it's traveling downward, so it is following this parabolic shape here. And that parabolic shape has a radius of curvature. And in this problem, radius of curvature is what we're looking for between the center of mass of the rocket and the center of that circle. And we're supposed to find the rate at which the velocity increases. So not the horizontal velocity acceleration, but this downwards acceleration. And we're now going to be getting into some curvilinear motion because we're also looking for omega here as it rotates around. And then we're looking for the total acceleration of the rocket. We're not going to finish this today, but I want to start breaking down the given problems and kind of some ideas where to go. If you are super high achieving, not even high achieving, overachieving, you can take a look at this problem, see if you can solve it for yourself. But I'm going to be getting into that next time. I would suggest start working on the homework problems instead. I'm going to simplify this down. So know that at this end of the circle goes all the way in, but I want to have space to write. So in this case, we're not given time 1, time 2. We just have this one instantaneous position in time. So if you want to think about that as like a little small fragment dt, so we can know instantaneous velocity and acceleration. This problem is more about the coordinate systems and organizing them all together. So the acceleration for the horizontal is 20. This would fit into an XY coordinate system. It's completely defined by the space around it, objects that are not moving, not any kind of velocity. So we can already see here that we're overlapping coordinate systems. And the problem statement also gives us that the vertical acceleration due to gravity, where this is in space and whatnot, is 30 feet per second squared. So that's different than other kinds of gravity because it's really far up. I'm going to change this horizontal to X now that we do have a defined coordinate system. It is okay if you don't define this coordinate system, but write horizontal and vertical. That would be totally acceptable. But I want to emphasize the overlapping coordinate systems here. So the velocity of the rocket, its magnitude is at this angle. Notice again that this angle is defining from space. It is defining from horizontal. So we can have a velocity in the X direction and a velocity in the Y direction based on cosine of 15 and sine of 15. This is not normal and tangential. So the first thing that we're looking for is the radius of curvature. When you think radius of curvature, think of normal acceleration. If you do not have normal acceleration, that would be the first thing you want to look for. But thankfully, what we do know is that we have this angle here. You know, I don't know how much more I want to get into this problem. So I'm going to re-say all of this next time. Yeah, let's be done for today. We'll just take this into account. If it was Monday, Wednesday, Friday, we'd like take minutes to get started. Don't forget to look at the homework that I've posted. I'm going to update Canvas to match the new grading rubric. I will see you guys on Thursday. Yes. Yeah. Great question.
How long, and then obviously that causes the
Yes.
magnitude change.
That really is a good question though, because
So it's tangential always constant?
Nope.
Or is it flip-flops?
well, sorry, tangential is always